Assalamu alaikum, dear students. We're back with another video lesson. If you remember in the previous video lessons, we're talking about transformers. Normally, we were talking about primary and secondary transformers. And of course, we talked about the conversion ratio as well. And of course, we said that one of the equations that we used was V2 over V1 equals to N2 over N1. And of course, you can take the reciprocal of all these, like the two sides of the equation and all that. And then we ended up, let's say, at this. And of course, then after that, we stopped right here. But let me just remind you, or start going from the top of this page. And that was, of course, real transformers are not perfectly efficient. What do I mean by this? Now, remember this, we said when we are talking about transformers, we normally talk about ideal transformers. And if we talk about an ideal transformer, that means the power input it is equal to the power output, because normally you can say in real world, no transformers are ideal no matter how much you try. Of course, you can have, let's say, an efficiency about 99%, could be even 0.9, but of course, it will be very difficult to have a transformer that their input power it is equal to the output power. And of course, we said that is for several reasons. One of them, if you can say, because of, you can say eddy current, and of course, and also because of the resistance of the wires that are basically winding, or you can say resistance of the wires of the coil as well. So basically, when we talk about transformer equation, we assume that no power is lost. So remember, that is between the transformer's primary and secondary coil. That was for an ideal or ideal transformers. But in real transformers, you can say, typically have efficiencies ranging from, let's say, 90% to 99 or just to 99%. That would be the efficiency of, let's say, real transformers. So if that is the case, where does the power gets lost in a transformer? We said, of course, because of the small current induced, let's say, by the changing magnetic field. So basically, when there is a change in current in the primary, or you can say secondary, when there is a change in the current of the primary coil, this change, of course, causes, you can say, a change or varying, let's say, a varying magnetic field. Let's say this varying magnetic field will be transferred to the second coil. Then, of course, induces a current. This current also induces a magnetic field. This to oppose one another. You can say, of course, this opposition, you can say, loses, you can say, or kind of like wastes part of that energy. And of course, you can call this one eddy current. And another factor that wastes the power was because of the resistance in the wires of the winding, you can say, which of course changes to heat energy. If you normally, for example, let's say if your phone, let's say charging, and if you go and touch the charger of the phone, right, remember it has to be sealed as well. So you will feel that, of course, the charger is, or let's say after some time, after it is being used for a while, you can see or feel that the charger is being a little bit, let's say, warmer than the surrounding, or it is hot at some times. And of course, that means basically energy is being lost due to, you can say, or to thermal energy. So we can say the power loss is to the resistive heating in transformer line. It varies with what? With I squared times the resistance. And of course, we said how power is transmitted over long distances and why. We said at high voltage, if you want to send power, let's say, over long distances, we'll have to use, let's say, or send this power at a high voltage. And then, of course, why high voltage? Because the power that we have, it is fixed, let's say, it is a constant. So once you increase the voltage, the current decreases, and once you decrease the current, the power loss will be reduced, you can say. Why? Because power loss is equal to I squared times the radius. So the smaller the current, let's say, the more the power you have, let's say, saved from being lost. And of course, the relationship between these two, or if we ever ask, like, if you have the chance to, let's say, reduce the current to half and the resistance to half, which one has a bigger effect or impact on the power loss? Of course, it is the current, because the current is squared here. So because we'll say power, that is equal to a power loss is equal to current squared times the resistance. So we'll say by reducing the current by a factor of 10, the power loss is reduced by, you can say, a factor of 100. So we went through all that. And of course, high voltage is stepped up. Let's say now high voltage is stepped down once it is close to the homes and supplies. So let's say domestic, you can say for domestic uses. Normally, You can say for most of the countries 220 volt, and of course some other countries it's less than that, could be 110 or 120 depending on, let's say, the country. Okay, now this is where we stop. So this is basically the actual or the beginning of this lesson here, and that is basically, you can say, the ignition coil in a gasoline engine is a transformer. But what type of a transformer? You can say it is a step-up transformer. What does exactly this system do? Normally we have, let's say, the engine of a car, and of course, let's say this gas, of course, is spread into, let's say, in between, let's say, the piston, of course, there is a piston here and all that, yeah? So this gas will be spread, and of course, when these pistons, for example, move up, of course, there is a high pressure onto the gas, then this spark plug, you can say, has to cause or has to produce a spark so that this, let's say, this fuel will ignite, and of course this ignition, of course, will cause something like an explosion that sends the cylinder, you can say, downward. And this cylinder, of course, it is connected to other parts of the engine, the crankshaft and all that, you can say, and then starts to rotate, let's say, the crankshaft, and of course then this rotation will be transferred to kinetic energy for the tires, and this is how the automobile or the car can move. But let's dive a little bit deeper and see how it exactly works. Okay, so we said this spark is basically, you can say, it is we use a, let's say, step-up transformer to get the job done. And so how does it work? We'll say the ignition system uses a transformer, okay? And this, of course, is called the ignition coil. So remember this, which is basically an electronic ignition here, to convert the car's battery, which is basically 12 DC volt, to a potential difference that is large enough to cause a sparking between the gaps of the spark plug, you can say, or let's just say the gaps of, let's say, the spark plugs here. So basically, you can say it converts 12 DC volt into, let's say, between 40,000 to 100,000 volt. So how can you convert 12 DC volt, okay, direct or just DC volt, into 40,000 or 100,000? Of course, that is basically stepping it up, yeah? So of course, in this case, you will need a step-up transformer. So what exactly do we need to do? The goal is to ignite the fuel at the exact moment when the expanding gases can do maximum amount of work done. So when can we do that? You can say when, you can say, the piston is moving upward, so you can see compresses the gas and all that, okay? And then right at this point here, then if there's a spark and these gases, and of course the oxygen and let's say the fuel, so of course one spark can ignite this, and of course then it can move the cylinder downward with the, you can say, with a maximum torque in this case. So that is basically what we have. So how does it work? A photoelectric detector that is basically called a crank angle sensor uses the crankshaft's position to determine when the cylinder's contents are near maximum compression. So when it gets near maximum compression, of course, a signal will be sent to the car's, you can say, computer or automobile's computer. If that is the case, then upon receiving the signal, this circuit, of course, will be closed on, of course, right? Now, this circuit is not manual, it is automatic because it is connected to the, you can say, to the computer or car's computer. Normally, we call it just the brain of the computer, let's say, or just, let's say, the main circuit for the computer, the one that, let's say, do all these jobs. So simply, the computer's automobile, you can say, automobile's computer. So what happens next, okay? So then once this happened, this primary circuit, of course, will be closed, you can say, and if that's the case, causing the current in the primary coil to rapidly increase. So if the current rapidly increases, what do you think will happen? That is for primary here, okay? So we said, so in this case, you can say the power input is fixed or constant. So if you increase the current, let's say the voltage will decrease, yeah? So we can say that is for the primary, yeah? What about for the secondary here? Or something better, we can say that, yeah? Forget what I just said. Now listen to this one here. Because the current is rapidly changing here, so this rapid change, of course, it causes, let's say, a rapid change in the magnetic field over the second coil, or you can say for the secondary coil. And of course, this rapid change will produce or induce a very high voltage, and of course, which is about, let's say, 40 to 100,000 volt. Or you could just say, because the change in the magnetic field on the primary side is so quick, the change is basically induces a very large electromotive force, which is basically ranging from 40,000 to 100,000 volt. This electromotive force applied across the spark plug and creates a spark, okay, that ignites, let's say, so this spark basically ignites the ignites and burns the fuel, and of course that powers your automobile here. So I hope you really understood this. Let's summarize it one more time real quick. So we said basically this ignition coil so that it causes spark, and of course in order to cause a spark we'll convert the car's 12-volt battery into something, let's say 40 to 100,000 volt. Don't forget this. If we're basically stepping up the voltage, so we need a step-up transformer. So how does it work? The purpose, you can say, or the intention is we'll do this, or we'll kind of like light the gas and the fuel, let's say, when there is the possibility of doing maximum work. So how do we do that? Well, there is a sensor basically. It senses, for example, like when the cylinder and its content, let's say, are like at a point all these gases and compressed here. So once this happens, of course, this let's say sensor sends a signal to the car's let's say computer. Then this computer will close the primary circuit. The current will change very rapidly. This rapid change of the current will cause a very rapid, you can say, change of the magnetic field in the secondary coil. This rapid change, you can say, of the magnetic field in the secondary coil will produce or will induce, let's say, a voltage that is between 40,000 to 100,000 volt. And of course, when the voltage is this much, then of course there will be a spark right here, and then this spark, of course, is enough to ignite the fuel and the gas and, let's say, and all that. Then of course it's like an explosion. Now it pushes, you can say, the piston downward, and this downward movement will be converted, because it is connected to crankshaft and all that, will be converted to other parts of the engine where it will be used, let's say, to start or to move the car, let's say, or just to kinetic energy, if we consider it that way, so that the car now can go forward or backwards here. But mostly we use it for forward, as you can tell. Okay, so this is the purpose of this ignition coil, and of course there has been questions about this, and there will be. So what is exactly, if you're willing or if you want to change a 12 DC volt to, let's say, 40,000 or 100,000, then of course you need a step-up transformer. So this is how. If not, you will not be able to do that. Okay, that was for, you can say, the ignition coil here. Now let's talk about energy here, okay, or energy transfer. If you want to transfer energy, how would you normally do that, okay? Now, of course, here we can say electricity is transferred from power stations to houses and, let's say, to factories, and of course we can say, but how do we use that? But of course by using cables, yeah? Okay, cable of, you can say, a network of cables actually. So because these cables stretch for hundreds of kilometers, you can say, it is resistance, because sometimes it's from one city to another city that are very far, let's say, and of course these cables or these wires have resistances, okay, which is quite big, and of course gives rise to a loss of part of the energy that is carried. So we can say, what does the energy loss depend on in power lines? Of course, the energy loss depends on two factors here. We can say, or using the equation power loss equal to I squared times R, so we can say it depends on the resistance of the wires, and also depends on the square of the current as well. And of course, you can say it is directly proportional to both of them. So the power loss is directly proportional to the resistance of the wire. In another word, the higher the resistance, the more the power loss. That is 1 second. It is directly proportional to the square of the current. So in another word, the bigger the current, the more you can say the power loss by, remember, you can say by the square of the current here. But remember this, okay? So if we double the current, then let's say if we double the current and then double the resistance, which one of them would cause a bigger power loss? That of course is the current, because it is squared. If I ask the question in a different way, we'll say if we have the resistance of the wires and if we have the intensity of the current that is passing or flowing through the wires, which one of them would save a better power, let's say? And of course it is the current. Why? Again, because it is squared. So we'll say power loss equals to current squared, then multiplied by the radius. And of course, if we talk about energy here, let's say energy loss equals to, we've learned that energy equals to power, or you can say the rate of, that'll be, okay, let's talk about energy. So we do know that, okay? We can say energy is basically equal to power what? Power times the time. But if we talk about the energy loss, okay? So of course this power becomes the power loss, and that is current squared times the radius, and then times the time. Okay, so that'll be the equations that we, all right, or you can take a look these are for the energy loss and what do they depend on. And we have also mentioned that which one has a bigger effect? Is this the resistance or the current? It is the intensity of the current because it is squared. So take a look at these study tips. First one says the power loss is directly proportional to the resistance of the wire and to the square of the current. So don't forget, it's just not the current, it is the square of the intensity of the current. So power lost, we can say, is basically current squared times the resistance. And of course, reducing the current has a bigger effect. Now, another, you can say this point is also related to the last part, says the current has a bigger effect in energy losses compared to that of resistance. So don't forget, yeah? Okay, because the larger you can see, because it is squared, of course, so it will have a bigger effect. Now, so going back to answer this question, how do we send, let's say, power over, let's say, over long distances? We'll have to use a step-up transformer to send power, let's say, over long or very large distances. Why? Because once you use a step-up transformer, remember, the power that we use, it is fixed, let's say. So the power that we are using, we do know that power equals to what? Power equals to, that is current times, you can say, the voltage here. Okay? Current times the voltage here. So now let's say this value is constant, so it is fixed here. So why do we need to use a step-up transformer before we send it? Because if you increase the voltage at the same time, the current will decrease because this value is constant. And by doing this, all right, you are decreasing the current. And of course, decreasing the current will have a lot to do with this equation, power loss, okay? Power loss, it is basically I squared times the resistance here. So by decreasing the current, you're basically saving power from being lost in here. So this is why it is very important before you send the power to step up or use a step-up transformer to increase the voltage so that the current will be lower, and this of course will help reduce the power loss. Okay, what about when we get close to, let's say, the or at the destination, what transformer do we use? And of course, we will use a step-down transformer. Why? Because the voltage that you're using, of course, it is too high. It is not safe. It is not safe for the equipment or the electrical appliance as well. So you will have to lower that voltage so that you can use it safely, okay? So we'll use a step-down transformer at the destination, you can say, or for domestic uses, you can say. Okay, now, what can also reduce the energy loss, okay? By the way, it says we can also reduce the energy loss by what? Let's say one of the factors that the power loss depends on, or you can say affected by, is the resistance of the wire. So what can we do to reduce the resistance? By using thicker, let's say, power lines. And of course, we've learned that in, you can say in grade 11 and all that, the thicker the wire, the less the resistance, the less the power that is lost. And also we can use wires, or you can say wires of lower resistivity as well. So for example, instead of saying a metal that is not a very good conductor, we can use a metal that is a very good conductor, because the better the metal in conductivity, that means the less the resistance. That will also, you can say, save some powers. Okay, now we have another question, says, explain why transferring energy with high potential and low current in some practical, let's say, is more practical, you can say, than transferring it under low potential and high current. Okay, so we've mentioned this a lot because it reduces, or if you use a high voltage, that means the current is low. If the current is low, that is reduces energy loss due to the resistance, you can say, in the transmission line. Also, power is proportional to the square of the current as well. So minimizing the current decreases the power loss, you can say, and of course, making the process more efficient here. Okay, now let's talk about transferring energy, you can say, or transfer efficiency. Yeah? So what do we mean by efficiency here? For example, you have two machines. Yeah? You say one of them has a better quality in the other one. Yes? What exactly do you mean by that? Now, in physics, sometimes we say it is one device is more efficient than the other one. What exactly do we mean by this? When we say one device is more efficient than the other one, that means this device is let's say, wasting less energy compared to the other one. So let's say you have two devices, one of them gets too hot, all right, and exactly does the same job, and the other one, it doesn't get hot. So if clearly the one that gets too hot, that means it is, let's say, losing or wasting a lot of energy. At least part of that energy will be converted to thermal energy. That is a waste, obviously. Okay, and then the other one does not heat up that much. Or in a different way, let's say how much of the energy that you give to this device will convert it to something useful. That is another way you can say this efficiency. And of course, the other way that we use, of course, we'll say the ratio of the energy that is basically received to the energy that is sent here. And of course, the bigger that ratio, that means the higher the efficiency, or another way you can say the better the device in terms of saving energy or not wasting it. Okay, so we'll say transfer efficiency, it is a ratio of the power that reaches the city, could be a factory, to the power that is sent by the power station. So we can just simply say transfer or power efficiency, we can say it is basically the energy that is received, all right, and then divided by the energy that is sent. And if we want, because normally we find the efficiency in percentage, so we'll say multiply by 100%. And also remember this, because it is a ratio, whatever the unit that you're using, they cancel out both on top and bottom. So ratios have no unit, you can say. So transfer efficiency, these are the ways that we can do that. We'll say the power sent minus the power loss divided by the power sent again, multiplied by 100%. But of course, we can say the power sent minus the power loss, isn't that called power received as well? So we can either use this based on the content of the question. If power sent and loss were given, or one of them is unknown, we can use this equation. If it talks about power received, we can use this equation here over power sent multiplied by 100%. But before we go into this more, remember this. Whenever that is power sent, we'll use this equation. And then once you use this equation, we mostly are going to find the current here. And then once you found the current here, of course, we'll use this, the current into this equation, we'll find the power lost, okay? So once we found the power loss, we can use this equation. Once you're done with this, of course, you can have the power received if they ask for the power received. If not, you could just use it into this equation so that you can find the efficiency right here. Okay, so of course, now we are going to get into some questions, but just remember, these are the equations that we're going to use for the efficiency. And of course, this is transfer and transmission system, you can say. So what does it say? Electric power is transmitted from power plants to houses and factories, let's say, by means of network of cables and, of course, transformers as well. So you can see this is where it comes from, the power generation, you can say, or the power plant, right? And then from this, of course, you will step it up to, let's say, 240,000 volt. And of course, you can use more than one transformer along the way to step it up more and more until you get a very high voltage. And of course, you can see that whenever you see these high voltage transmission, they have to be far from, let's say, the ground or anything that can reach them for safety purposes, of course. And then after it gets close to a factory or houses, let's say, then we will have to use a step down transformer so we can, let's say, use this electricity safely without getting harmed. And of course, that is one of them, you can say. So we will step it down one more time so that we can use this range, which is about 240, depending on the country, and that is the voltage that we use normally. Okay, now that was for, let's say, transferring the power. So if you ever want to transfer power over long distances, you'll have to step up the voltage, let's say lower the current so that the energy or the power loss will be less. Okay, now we have a few questions here. These questions are very easy. The first one says, when transmitting power over long distances by reducing the current by a factor 10, the power loss is reduced by, because it is power current squared times the radius, so of course you'll be saving the power by 100 or factor of 100. Okay, the next one says electric power is transferred from power stations to a residential area with what? Okay, so how do you send or transfer power from, let's say, one place to another? Of course, you'll have to use a high voltage and low current. Again, why? Yes, so that we can save the power from being lost here. Okay, now take a look at this question here. It says the power in the secondary coil of a power station is 1 megawatt. Mega, that is 10 to the power 6. The station sends the current to the city by means of lines of 10 ohms, let's say 10 ohm resistance, under potential difference of 1 times 10 to the power 5 volt. Calculate the transfer efficiency. So how do we approach questions like this? It's very important. So please take a look and let's do it together, hopefully, because by doing one or two questions, of course, you can say you'll just get the hang of it. So you will know how to do this. So the power is one of the things that we have, the power sent, you can say, or the power from the power station, the power in the secondary coil of the power station is 1. So we can say the power sent, okay? Because this will be the power that comes from the power station, or the power station, let's say, okay? So that is basically 1 megawatt. So 1 times 10 to the power, how much is a mega? 1 times 10 to the power 6, that is basically watts. Okay, that's one thing. Says the station sends the current to the city by means of lines of, let's say, 10. So we have resistance. The resistance is what? Is 10 ohms, you can say. Under potential difference, so we have the voltage here. What is the voltage? That is 1 times 10 to the power 5 volt. What is the question? The question says, calculate the transfer efficiency here. So how do we find the efficiency here? We'll say efficiency, let's do it here, or transfer efficiency equals, we said that, normally equal to what? Equal to power, okay, power what? Power sent minus power lost, and then of course divided by power sent, and then multiplied by what? By 100%. Very, very good. Now, so do we have the power sent? Yes, which is 1 times 10 to the power 6 watts. That is mega. So we have this, but do we have the power lost? The answer is no. So how do we find power lost? Okay, now regarding this, we can say the power loss is equal to what? Remember, we said what is the equation that we use to find to find the current? Or before that, let's say power lost, okay, equals to what? Equals to current squared times what? Times the resistance. So we do have the resistance, but do I have the current? The answer is no. So how can I find the current here? We'll say for the current, if you do remember, we said we'll use one equation, yeah? So here we're going to use this. Say power sent, okay, equals to current times, you can say the voltage here, okay? So now I have the power that is sent, I have the voltage that is sent with, okay? So I can find the current that is sent with as well. So I can say the current that is equal to power sent divided by the voltage here. So what is the power sent? That is 1 times 10 to the power 6, and then divided by the voltage, which is 1 times 10 to the power 5, yeah? Okay, so of course, you do this one here, that is 6, then that is 5, obviously. You get 10 amperes, correct? If not, you could just do this one. That is basically million over, let's say, 100,000. So of course, you get 10 amperes. That is the power there. So now we have 10 squared, just like this is the current, okay? So 10, but 10 squared multiplied by the radius. Why radius? This is resistance. Okay, so in this case, of course, 100 times 10, that is going to be 1,000. 1,000 what? That is obviously watts. Okay, this is the power loss. So now I can do the, I can go back to this. Okay, I can say power sent is basically 1 times 10 to the power 6 minus, here the power lost is 1,000, you can say. And of course, divided by 1 times 10 to the power 6 here. This is basically 1 million minus 1,000, that is 999,000, you can say. So divided by this, of course, let me not forget the 100%. So once you do this one, of course, you will get the percentage. Let's see what was the percentage, okay? So in this case, I'll have to move down here. So it is obviously going to be 99.9%. 99.9%. So 99.9%, let's see. And of course, this is, you can say, the transfer efficiency. If you want to write transfer efficiency for this, let's say the power transfer. This is how you will do that. And of course, we said there's no unit for this because it is a ratio. That would be the final answer. I hope the answer or the idea is very clear because this is how you do that. Okay, now the next one says calculate the power lost as heat in the wire of resistance of this much traversed when traversed by a current of 50 amperes. So there's nothing in this. You just multiply the two. Power loss is equal to current squared times the radius. You just do the math and you'll find it. Now take a look here. Question 2 says, if a power of 3 megawatt, how much is a mega? That is 10 to the power 6, is sent along the wire in item 1 in the first question. Calculate the power at the end terminal of the wire at the transfer efficiency. So here you find the power loss, which is 3 times 10 to the power 5, that is watts. Okay, and then if the power sent is 3 megawatts, so you could just use the equation here. Power sent minus power loss divided by the power sent, or if not, you could just say power received divided by the sent power sent multiplied by 100%, you will just find the answer, and that's all of it. Okay, and of course these are some Wrya questions. These are very, very important. I'll only try to do one of them here. It says the power in the secondary of a transformer is 1 megawatt. The station sends the current to the city by means of the lines. If the power loss across the line is 1, no, that was not the question I wanted to do. This one here. Okay, so these are very easy, by the way. Just you know, like you do the math and that's it. But I'll try to do this one here because there's an idea in this, and I will show you or tell you both ideas here. So it says an electrical power station sends 10 to the power 6 watts, that is, you can say 1 megawatts of electric power to a city. If the transfer efficiency is 90%, what is the power loss in the conducting wires? So there are two ways to do this. So let's do the common way first, okay? And then after that, I'll show you another way, which is very easy. You can always do that as long as you understand the question well enough, and then you can use the same method. Okay, so now here we have the question, yeah? Transfer efficiency, you can say, is basically, we can say power sent, that is equal to power sent minus power lost, okay? And then divided by power sent, and then we can say multiply by 100% here. Okay, now that is the equation basically. So it says, but take a look here, it says, if the transfer efficiency is 95%, if that is the case, of course, we can just bring this one here. So we'll say the transfer efficiency is 95%. Percent, it is the same thing as if you say 95 over 100, okay? And if that is the case here, what is the power loss in the conducting wire? So take a look at this equation. It says the electrical power station sends 10 to the power 6. So we'll say power sent is 10 to the power 6 minus power lost, okay? And then divided by 10 to the power 6 here. So of course now, you can do, let's say some, what do we call it? Some simplification with this tree here. If not, you could just do the math here. But before that, 95% it is, isn't it equal to 0.95? Yes. Okay, what else do we have left? So 10 to the power 6 minus power lost, okay, divided by 10 to the power 6 here. Now, of course, you're going to do cross multiplication here, but these two are together, don't forget. So we will say 0.95 times 10 to the power 6, it is equal to 10 to the power 6 minus power lost here. Okay, so clearly this power loss will go to the other side, and then you will bring this one here, because there's a negative, don't forget. So we will say power lost, okay, it is equal to 10 to the power 6 minus the product of this two, which is 0.95, whatever the answer is. You just write it down and do the math, subtract them, and of course you will get the answer. And I believe it was about 5 kilowatt, if I'm not mistaken. Okay, but that is one of the first way. You just do the math, and of course you will find the power lost. That is one of the way. What is the other way? Okay, so we can say the other way is this. Okay, now bear with me. See how simple the idea is. But of course, if you didn't get this one, just go ahead with the first method, and that's all of it. So it says, take a look, if the transfer efficiency is 95%, so the transfer efficiency is 95%. If that is the case, what is the power loss? Can I say the power loss that is about 5%? Yes, if it is 5%, of course, we can say it's about 0.05, you can say, if that is the case, yeah? That is this. But it says what? If the transfer efficiency is this much, what is the power? So now, this is how much, or the percentage you can say that is lost, correct? But this percentage is lost of what? Of this one, of the power sent here. So remember, this is the power that is sent, which is 1 megawatt, or 1 times 10 to the power 6. So we can say 95% is sent to the city or to the destination, but then only 5% is lost. So we could just say 5% of this much, that is the power that is lost, and that is as simple as that. Okay, so you could just say 5% or 0.05 times this one here, and of course it gives you the right answer there. So we can say 5% times the total is clearly 10 to the power 6, and of course you do the math, you will find the answer. So let's see, that is 0.05 multiplied by this much, okay? So obviously it is going to be 1, 2, the other way. So 1, 2, that is clearly about 50, yeah, or 5 kilo, 50, yeah. So the answer in this case, it has to be 50 kilowatts. That is, we can say the power that is lost. I hope the idea is clear, yeah. Remember, the power sent, that is all of it, you can say, 10 to the power 6. Now, the transfer efficiency is 95%. That means 95% is received, or let's say delivered, but then only 5% is lost. So we'll just say, what is 5% of the total? That would give you the power that is lost, okay? And that was the answer to this, of course. We said it has to be 4A, yeah? Okay, so you choose or do the math, of course, you'll get the answer. Just wanted to double check because I don't have, like it didn't do the calculation. I would just wanted to double check. Okay, now there's another question which is also very, very important, guys. And how do we do this one here? Okay, so take a look. It says a generator supplies, let's scroll up just a bit more. Okay, it says a generator supplies 5 times 10 to the power 3 kilowatts, okay, of power. The output is, the output electromotive force is 4,500 volts. Before it is stepped up to 510 kilovolt. The electricity travels 6.44 times 10 to the power 5 meter through a transmission line that has a resistance per unit length, guys. So what does it mean, resistance per unit length? That means just like what we had before in, let's say, a previous chapter, let's say. So of course, we had turn ratio, let's say, or let's say N over L, yeah? So here we have the resistance per unit length. That means resistance divided by the length. But we do have the length. And of course, take a look at the unit as well. That must or should give you an indication as well. So here's a question. How much power is lost through the transmission of the electrical energy along the line? So let's see how we can solve this question together. Okay. Let's get it back. Okay. Okay, so what are the information given here? Okay, the first one here, as you can tell, we have, it says generator supplies this much kilowatt. So this is, you can say, the power. Okay, we can say the power that is sent here. So the power, you can say the power that is sent. How much is this? That is 5 times 10 to the power 3 kilowatts. 3 kilowatts. Can I convert this one to, this kilo is another 3, yeah? So that would be about 5 times 10 to the power 6 watts. You can say 5 megawatts as well if that was a multiple choice, let's say. The output electromotive force is 4,500 volt before stepped up to this much, yeah? So we can say the voltages that are given here, one of the voltages 4,500 volt, the other voltage, let's say V2 here. By the way, these V1 and V2 doesn't mean for a transformer, yeah? This is just 1 and 2, like this before stepping it up. This is after stepping up, which is 510 kilovolt. Can I just say 510 times 10 to the power 3 volt? Yes, very good. The electricity travels this much. So we can say the length is 6.44 times 10 to the power 5 meter through a resistance. Watch this. It says resistance per unit length. Don't forget, which is 4.5 times 10 to the power, that is 4 ohm per unit meter. Okay, so how much power is lost through the transmission of the electrical energy along the line? So let's say this is basically the line that we have. So first of all, let's say this is a transformer. After stepping it up, here's let's say what we have in here. So remember this. We can say this is the voltage before stepping it up, and this is the voltage after stepping it up, let's say before and after. Okay, so, but what is the power that is sent with? The power doesn't change. The power is always fixed, yeah? Increase or decrease the voltage, assuming the transformer is ideal, the power is still the same here. So, okay, so what is the first part? It says, how much power is lost? If we want to find the power loss, we do know that power loss equal to what? Equal to current squared multiplied by the radius. So how about, let's start with the radius here. Do I have the radius? The answer is no, but I do have something else. I have radius per unit length. So how can I fix this one? Well, for the radius here, if I remember this, yeah? If I divide the radius by the length, then of course I'll be able, after cross multiplying and all that, I'll be able to find the radius. why am I saying the radius? These are the resistance, by the way. I don't know why, but still, these are the resistance of the wire here. So we'll say resistance divided by what is the length of the wire? The length is 6.44 times 10 to the power, that is 5 meters. It is equal to, I think I have no space in here. I'll go do it over there. So let's just say, okay, we'll do it here. So in this case, I hope I have enough space now. Resistance over the length equals to that much, yeah? So how about if I just do it right away? Divided by, what was the length? That is 6.44 times 10 to the power 5, okay? And then equals to 4.5 times 10 to the power negative 4. Oh, did I write negative 4 here? Negative 4, and then that is basically, so you do the math, you cross multiply, you'll find the radius. So what is the radius here? It is equal to this much ohms here. Now, ohm alone, okay? So let's see what is the answer here. Okay, so the answer for this, that is basically 290. Okay, did I go too far? No, okay. I don't know why I have this. Okay, so the answer we said it is, not this one. Okay, so 290 was. Let's write this one nicer. 290 what? 290 ohms here. Okay, that is the first part of this. Now, here comes, like, what about the second part here? How do I find the current here? Remember this, yeah? So the power, or you can say the power, we said it is fixed, so it doesn't change, yeah? So after, by the way, which voltage do I need to use? The one that the voltage, for example, the one before stepping it up, or the one that is after stepping up? Well, you will have to ask yourself a question. Like, remember this, the power doesn't change, yeah? Which voltage and current is the one that is being transferred? Is it the one before stepping up or the one that is after stepping up? If it is the one after stepping up, because this current, of course, will, or the amount of the current here would add up to the power that is lost. So in another word, I'll have to use the second voltage. I'll repeat the idea. Why the second voltage, not the first? Because after you step up the voltage, then that is the voltage that you are sending, let's say, the power with, okay? So voltage times the current here. So this is the voltage that you're sending, it is V2, the power is fixed. So now I can find this current here because the current that is passing or flowing through the cables, that is the one that obviously will be or causes the loss in here. So in order to do this one here, we'll say power that is sent, that is equal to current times the voltage, or you can say V2 here, because that is the one that we've stepped up, and then after that, of course, we'll use that one here. So we'll say the current here, that is equal to the power sent, and then divided by the second voltage here. What is the power that is sent here? The power that we sent, it is clearly 5 times 10 to the power 6. The voltage that is also been sent, that is, not this one. Remember, the voltage that is stepped up, which is basically 510. Let's write this one nicer. Oops, that was too much. Okay. Let's, okay, so 5, we can say 510. Okay, so 510 times 10 to the power, remember, it is 510 kilovolts, so kilo is 10 to the power 3. So you do the math, of course, you will be able to find the current here. And to save some time, I'll just go and tell you what is the current here. The current that we have, clearly we need to go downward a little bit. The current that we have, it is 9.8 amperes. 9.8. Oh, okay. 9 what? 9.8 amperes here. So this is the current that is sent with, you can say, yeah? There's the voltage, and this current is 9.8. This is basically the current that is sent with. And clearly, the current that is sent with is causing the power loss in here. So we'll say power loss, all right? Power loss or power lost, you can say. That's the same thing here. It is 9.8, but don't forget, this is squared multiplied by the resistance, which was 290 ohms here. So you do the math, of course, you'll find the power loss. That is the first part of the answer. That is going to be this much watts, or in watt. Okay, now that is for this. What about for the second part? It says, how much power would it be lost through the transmission line if the generator output electromotive force were this much here? And what does this answer tell you about the role of the large electromotive force here? So what is the question here? It says, what would be the power loss if we did not step up the voltage? Clearly, if you don't step up the voltage, the current will not reduce. Or you can say if the current is not reduced, the power loss will be higher. Okay, so what do we do here? So basically, we're doing exactly the same step here, but the only thing that we will change is this. Let's use a different color perhaps, yeah? Okay, so we can say, or going back to this, we have the resistance, which is fixed here. For the power sent, instead of using 5 times, where's the other one here? Instead of using V2 here, we're going to use V1 here. And what was V1? It is clearly 4,500, yes? 4,500. And of course, if you're going to do this one here, you will get or receive, let's say, a different value for this. So in this case, of course, I'll have to move down again. So take a look. If we're not, I'll just do it here. If we're not going to, let's say, use the step-up transformer, so we'll have to use the voltage before stepping it up. That is V1 basically. And if that is the case, then the current you will get will be 1.11 times 10 to the power 3. And compare this one to the current that is there. You see, this current, by stepping up the voltage, will be reduced a lot. This current will be, let's say, way smaller, way bigger than this. And of course, the bigger the current, the more the power loss in this. So the power loss, of course, you can say, remember, current squared times the radius is still the same. Use that current, multiply by the radius, you get about what? You get about 3.6 times 10 to the power 8 watt, and that is about 360 megawatts. And what was the power that we sent with, let's say? It was 5 times 10 to the power 3 megawatt, which was about 5 times 10 to the power 3 kilowatt, which is about 5 megawatts. So imagine the power that you sent it is 5 megawatt, but the power that is lost, it is about 360 megawatts. So we can say the power that is wasted is way bigger than the power that is sent in this case. So of course you can say transferring the power over long distances or long range with this high current will be impossible because the amount of energy or power that is lost, it is just way too much. Okay, now let that be enough for this session, and of course we're going to complete the next session inshallah. In the next video we're going to finish chapter 6 hopefully, and then we'll start with chapter 7 afterwards if we have enough time. So make sure you practice well enough, and I hope you really understood this. If not, go back to the videos, practice one more time, you do it yourself and see how well you can improve. Till then, take care of yourself. Assalamu alaikum wa rahmatullah.